This is part 3 of the sequential and value function approximations. This module is going to be, I call it approximate dynamic programming with a computer science accent. So they refer to approximate dynamic programming as reinforcement learning. I'm putting this under the VFA segment of the talk, even though reinforcement learning has evolved to a broader. Think of this as Sutton and Bartow first edition back in 1998. So this is reinforcement learning in the style of computer science. Let's start with temporal difference learning. So this was one of the major cool phrases that Sutton and Bartow came up with in the 1990s. This is going to be how it was computed. Let's assume I'm in a state Sn at time n. I have the previous value function. So I'm going to have an iteration counter. So v bar n minus 1 is my previous estimate of the value function, but I'm in iteration n at state Sn. Now I'm going to say, okay, if I'm in state Sn and I take action xn, determined according to some rule, let's not worry about that, then I can get the downstream value function from being in state Sn and making decision xn. And then if you have randomness, because in computer science they didn't always have a random component, but let's say they did, that Sm function is the next downstream state that you would land in, and I'm going to use the value of that, again, using the value functions from iteration n minus 1. Let's take the one period contribution plus the downstream state and roll that all up into this variable called Vn of t. Now, the difference between the v bar n minus 1 as state Smt and this Vn of t, these are two different estimates of the value being in state S. Let's call it the old estimate and an updated new estimate. So the difference between these two is what's called the temporal difference. And by temporal difference, in computer science, the variable n was sort of a time variable, not t. So I put in t just because that's my standard notation, and maybe we have a finite horizon problem. But here the time variable is the iteration n. So this is effectively old minus new, and we can update our value function as the new value function v bar n is equal to the old value function v bar n minus 1 at state Sn, minus a step size alpha, a smoothing coefficient, could be a number like 0.1, times delta, okay? Times this delta that we just did. And that delta is the temporal difference. Again, it's the change in the value function over time. So this was called temporal difference learning. They call it TD0. I'm going to explain that just momentarily. Now, let's imagine, so Sutton and Bartow were playing a lot of games with this maze, the mouse in the maze problem. And the problem with downstream values is if you have a mouse in the maze problem, I don't win anything one step away. I might be sitting there in the middle of my maze, and if I just take one step, I don't get any reward. I don't get the cheese until I make multiple steps into the future. So what they did was to say, well, let's, instead of just going one step out, let's maybe use our quote-unquote current policy to simulate all the steps that I would make downstream. So now that I have a whole sequence, and at each of those downstream steps, I will get another temporal difference. Now, let's roll that up with a discount factor lambda. So lambda here has nothing to do with time value of money. It's an algorithmic discount factor. So I'm going to do a weighted sum of these temporal differences to capture the fact that the simple reality is that the rewards for a number of steps may all be zero. And I don't actually get anything real until I get all the way out to where I win the reward at the end of the game. So this is a cute little technique, but very much geared toward playing these games. So lambda equal to 0 means you only go one step out. So TD0 is temporal difference learning without the look ahead, whereas lambda greater than 0 means you are looking ahead. And people found, gee, surprise, surprise, lambda has to be carefully tuned. And that's going to be the case always when you have these crazy little tunable parameters. Now, approximating the value functions, temporal difference updates can be paired with any recursive estimation algorithm for linear or locally linear models. So we can do lookup tables, and we've already reviewed in the module on estimation, lookup tables with independent beliefs, with correlated beliefs, and hierarchical beliefs. We've also done recursive learning with a linear parametric model. And you can do it with non-parametric because non-parametric is basically locally linear. Where things get tricky is if you actually have a nonlinear model of VFAs, and in computer science, probably the most popular nonlinear model is neural network, because computer scientists will often say, oh, I have to approximate some function, just throw in a neural network, it'll approximate anything. So I want to talk briefly about Q-learning in SARSA. Q-learning was one of the early algorithms developed by Sutton and Bartow. In reinforcement learning, a Q factor is the value of being in a state and taking an action. So I have to cover some basic language that Sutton and Bartow came up with. Understand Sutton and Bartow tended to be motivated by these natural examples, like a mouse running through a maze. Maybe there's an animal, and the animal has a certain behavior. So in other words, imagine that you have a physical system, maybe it's a human, where it's already acting in some way, and the way that it acts is, you call it the behavior. So they called it sort of the default, how the system naturally acts as the behavior policy. And if you just stand back and observe it, you can sort of say, hey, by following the quote unquote behavior policy, let's use the real world behaviors. Like, for example, the mouse in the maze, might let the mouse run through the maze, 1,000 times. And then every point in the maze say, what percentage of the time did the mouse go in each direction? And let that be the behavior policy. The target policy in the language of Sutton and Bartow is the policy we're trying to learn. We would like it to be the optimal policy. This would be the policy that our algorithm is trying to compute. Now, a challenge arises is, let's say, imagine we're peeking into the future using the behavior policy. When you mix the behavior policy while trying to learn a target policy, bad things start to happen. I tried and failed to adopt the Sutton and Bartow language. I like to use the word learning policy, and this is the policy that you use while learning, okay? We often call it an algorithm. And so let's say you have some algorithm, maybe it has an exploration part, and you're using this algorithm to learn the value functions. Once you have the value function, you're going to use the value function to make decisions. That would be the implementation policy. So in my vocabulary, we have a learning policy, which is the policy when you're running the algorithm to learn the value functions or learn how to make decisions. Once you've done the learning and you turn the learning off, now you're ready to use your results, and I call that the implementation policy. Now, there's something called on-policy versus off-policy learning. On-policy learning is where you're learning the value of the implementation policy. Whereas off-policy learning, let's imagine that you're watching the mouse and as the mouse runs, you just take whatever the mouse does. You never try to tell it to do something better. And so it may follow a certain path that only finds the reward, 20% of the time, where maybe you would have a much better algorithm would learn to find the reward 40% of the time. Okay. Off-policy learning is when you're sampling actions according to the learning policy. Okay. Now, the learning policy is assumed not to be optimal. Generally, it's going to be very much explicitly not going to be optimal. Now, one of the things you have to do is, while you're designing the learning algorithm, you're going to have this issue of, I want to be in a state and take an action. You have two questions here. How do you choose what state to be in, and how do you choose which action? Now, the most standard thing is to say, I have some initial starting state that's just given to me. How I choose the action, that's going to be the behavior policy, the learning policy. Maybe it's random, maybe it's what the mouse does, that sort of thing. And then you take whatever action that comes out and you use that to determine the downstream state. Now, you don't have to do it that way. While I'm learning, I could just sample states at random. maybe I have a state I could never even visit, but if you just choose it at random, oh, sure, now I can visit it. If I had my nomadic trucker and I never have loads going to Alaska, but maybe I choose Alaska just at random and I can see what the trucker does in Alaska. Now, the CS community loves to talk about model-free versus model-based. Model-based means we have a mathematical statement of how the problem evolves that can be simulated in the computer. If you're using a computer simulation, you have a model of the problem. The one-step transition matrix is part of the model of the problem, as is the reward. Now, when you have a mouse running around, you may say, I don't even understand how the system is evolving over time, but I also don't even understand what the mouse is trying to maximize. So it's very common that computer scientists will say, well, I don't know the reward, and I don't even know the one-step transition matrix. So model-free refers to a physical process that can be observed, but where we do not have equations involving the evolution over time, such as the behavior of a human, the behavior of the climate, the behavior of a complex system, such as a chemical plant, or how disease spreads in a population. Q-learning is often described as model-free because it doesn't, it can be learned while observing a system. And also look at the policy. At the very bottom, I can take, let's say I have Q factors, which is the value of being in a state and taking an action. Now, notice that Q factor, I don't have any things of downstream values. I don't have to simulate my way to a future state. I just have a basic lookup of that function that says, well, if I'm in a state, in an action, this Q bar will tell me what to do next. And so the beauty there is that my policy, once I know the Q bars, my policy doesn't require that I know anything about the physical dynamics or the reward function. I just have the Q bar. Question is, how do you get the Q bar? So Q factors were very popular. It took a while for the computer scientists to realize that while they were always working with Q factors, the community of people doing dynamic programming and Markov decision processes and that sort of thing, we didn't do the value of a state in an action, we did the value of a state. And you can actually go back and forth between the value and the state. If you give me the Q factors, I can do I can do a max over A and get the value function so that you can go from one to the next. Now, updating Q factors, if I'm in a state Sn and for some reason I take action An, I have a reward Rsn of An plus a discount gamma times the max over A prime of Q bars at S prime and A prime. So what is S prime? Well, it turns out you had to simulate your way to some S prime. So if you're in a state Sn and take an action An, you then assume you have a transition model. That's a model, okay? You simulate your way to S prime, then use your Q factors to say, given that I'm in S prime, what's the best A prime that I would choose? That will give you a quantity Q hat, and now you take that Q hat and smooth it into the Q bars to get an updated Q bar. So you have to have a state sampling policy, which is how do you choose what state. Normally we're doing a trajectory following policy by following the state transition function, but you don't have to. You can just choose states at random. And then you have the action sampling policy, which again can be greedy. It can just be an argmax of the Q bars, or you can throw in some various noise terms or other sources. So there's a lot going on here. This was the early work in reinforcement learning. You can find all of this in the first edition of Sutton and Bartow's books. Now, at the end of your algorithm, your implementation policy, Sutton and Bartow would call it the target policy, is you take the Q bars, you take the argmax, and that's the action that you take. Now, the value of an implementation policy, you can just simulate this policy, and that is the value of the policy. We would like to find the value that works best. Computer scientists love to pretend that they're getting optimal policies. That's virtually never the case. We just don't get optimal in this world. Over many years and many people trying this, Sutton and Bartow started to realize that there's something that they came to call the deadly triad. So first of all, the Q bars have errors. They're not perfect, okay? And so there are errors in the Q bars that means that your policy, the argmax, is not an optimal policy. In fact, it may be well less than optimal. The bootstrapping. Number two, what you're doing is Q hat depends on Q bar. That's called bootstrapping. That's where you say, I'm going to take an updated observation of the value being in a state, but it depends on my estimated value of these downstream states. So this is where you're building a Q bar based on old estimates Q bar, a Q hat. You're getting a Q hat based on old estimates Q bar to update Q bar. That's called bootstrapping. And then finally, off-policy learning means that the way that you're choosing these actions is with some exploration policy or some way to encourage that you're visiting all the states. The three of these together are just a killer. When you have to deal with all three of these, it just doesn't work. And so Sutton and Bartow in their second edition has this quote: "The potential for off-policy learning remains tantalizing. The best way to achieve it is still a mystery." The problem is, if you don't use off-policy learning, how do you do learning? How do you force it to visit other states? I have an answer for you, and I already illustrated it back in my Nomadic Trucker when I did hierarchical aggregation. In all of my work on many real-world problems, I have never used exploration. I don't use discrete lookup tables. I'm always using some form of structure. At a minimum, I can do this hierarchical aggregation, which is stunningly powerful. And I always do on policy. I'm never doing off policy, but I do generalized learning, and generalized learning is the secret to making this work. Now, I still have come to the conclusion that uh, uh, making decisions based on Bellman is problematic. Okay, there are thousands of papers demonstrating various forms of ADP. I've written a bunch of these with my students. So the deadly triad helps explain algorithms for learning. VFAs do not work, but even when a VFA algorithm seems to work, and I have a lot of these examples, it's not good enough that this algorithm work well. It has to be a better and easier algorithm to work than any of the other three classes of policies. And this is where it really fails. I have a document, tinyurl.com, why Bellman does not work. It's a series of LinkedIn posts that pretty much walk through the steps of, you know what, Bellman's really hard. I've had my greatest success with Bellman, and I have had great successes with problems with a tremendous amount of structure. And so I've solved complex resource allocation problems, exploiting convexity and concavity. For these classes of problems, it has been very useful and better than anything else. But this is a tiny class of problems. And it's one of the reasons why everybody makes sequential decisions over time who have never even heard of Bellman. So for more on this, again, go to the SDA website at Policies and Value Function Approximations.